Okay, another lesson, 76. So after this, we'll have 10 to go. So we're doing well. We're going to get there. I was trying to do 2 a day. I don't know if you've realised that. And so with that, I've got, a couple. I've got 3 more from AS Maths to do. And then 8 from A2 Maths Mechanics. So this one's called Dynamics 1, actually, is what it's called. I've just called it Dynamics there, but it's supposed to be Dynamics 1. It's based on work from page 204. Talk through, I'll do the examples, then upload it all for you to Canvas. When we give a large push to a sledge on ice, the sledge begins to accelerate, okay, because there's no friction. The bigger the force that we apply, the bigger the acceleration. Acceleration is directly proportional to the force that we apply, which makes sense. Push it harder, it's going to accelerate more quickly. If we had a sledge of twice the mass, we would need a force twice the size to create the same acceleration. Okay, so double mass, double force to get the same acceleration from the first scenario, first paragraph above. The force we apply is directly proportional to the mass. Newton's second law of motion states that the resultant force acting on a particle is proportional to the product of the mass of the particle and its acceleration. So the force, the resultant force, is the mass times the acceleration. We measure force in newtons. 1 newton is the force required to give a 1 kilogram mass an acceleration of 1 metre per second squared. Using these units, Newton's second law is force is mass times acceleration, or F equals ma. Key point, if a resultant force F acts on an object of mass m, given acceleration a metres per second squared, then F is ma. Example 1, calculate the acceleration if the forces acting on an object of mass 25 kilograms are as those 3 forces there. Right, so what we've got to do here, we've got the resultant force is going to be 40, 15 plus 20 minus 7 plus 31, 23, which is 1691 on the top, 831 on the bottom. Okay, and then we want the acceleration, we've got the mass, and this is the resultant force. So the force is the mass times the acceleration. Notice I'm underlining the vectors, which are the force and the acceleration. So therefore, mass times acceleration is 91/31, and the mass is 25. So therefore, the acceleration is 91 divided by 25, 31 divided by 25. And I'm using the textbook to show that, to get the answer. Acceleration is 3.64 I plus 1.24 J. So the 3.64 is this answer, and the 1.24 is this answer. And they're the I's and they're the J's. So they're horizontal and there's the vertical. And it's metres per second squared. Okay. Key point. The equation F equals ma can be used in any direction. These should be underlined. Where F is the resultant force in that direction and A is the acceleration in that direction, in that same direction. Example 2. A box of mass 5 kilograms. Let's do that neatly. And weight 49 newtons. Well, if you've got 5 kilograms as your mass, what we've got, if the mass is 5 kilograms, remember the weight is mass times gravity. So it's 5 times 9.8, which is 49 kg. Okay, so that's where that comes from. Those go together. Rests on a horizontal floor. So let's put this down on the floor, like so. A horizontal force of 30 newtons is applied to the box. and the box is subject to a frictional force of 10 newtons when it's moving. Resolve horizontally and vertically to calculate the normal reaction R and the acceleration A. Okay, and down is the W. Okay, so what we've got there, well, it says resolve horizontally and vertically. I'm going to start by resolving horizontally, which is that way. So we've got, because there's an acceleration, in the previous lesson, the acceleration was always 0. But in this lesson, horizontally, we've got a plus 30, plus is going that way, minus the 10. They're the two forces. And that is going to be mass times acceleration. The mass is 5 and acceleration is A. Mass is 5. That's the 30 plus 30 minus 10. 30 is from the push forwards. 10's the resistance. And it's the mass times the acceleration. So therefore, the acceleration is going to be 30 minus 10 divided by 5, which is 4 meters per second squared. Yeah, you didn't need to resolve vertically. Not in this one. Sometimes you do, but not in this one. Vertically, I'll do it anyway because it said to do it. You've got that R equals W. Okay, so the normal reaction is going to be 49 newtons. Okay, when you have to do that is when the friction depends upon the normal reaction. But this one, they've told you the friction anyway, so you don't have to worry about that. Okay, so it's F equals ma. F is the net force, so it's all the positives and then subtract all the negatives, or take away the negatives, the total negative. Okay, last example here. A box of mass 10 kilograms and weight 98 newtons. So again, that is, the weight is mass times gravity. So it's 10 times 9.8, which is 98 newtons. And it's pulled upwards by a vertical string. So we've got a string pulling it upwards. We've got the weight acting downwards. That weight is 98 newtons. We have a tension in the string as it's pulled up. The block is decelerating at a rate of, so the acceleration is actually negative 2 meters per second squared. Find the tension in the string. State any assumptions made in part A. Okay, so again, it's being pulled upwards, but the acceleration it means the speed is slowing down. Okay, so we can say that the upward, we still take the upwards as positive, downwards as negative. So T minus 98 is mass, which is 10. So this is net force is mass times acceleration. So T minus 98 is 10 times minus 2. So T is minus 20 plus 98, which is 78 newtons. Okay. And that's all it is for that one. Part B. So the weight is more than the tension in the string, and that means that's sort of helping it slow down. That's why it's got negative acceleration. Right, B. This model, assumptions. We assume that the string is light. That means no light as in no mass. Okay. Inextensible, because that's a different topic altogether, if the string's allowed to stretch. I'm looking in the notes here as well. There's no air resistance. Okay. No wind acting on the particle, acting on the box. And we're actually assuming that the box is a particle. Now let's get this right. those ones are about they're the assumptions about the string. So the conditions are that we've got no air resistance or wind acting on the box. And also, it's the particle idea. The box is a particle. Okay. Particle with no size and doesn't spin, which again is a different topic altogether. In the A level, when I used to teach it anyway, they used to say name a couple of assumptions. So it was always light in an inextensible string with no air resistance. Box is a particle. Yeah. Okay. That's the end of that one. Oops, let's get that down.